Komodo dragons have iron-coated teeth. The teeth of Komodo dragons are coated with a coating of iron that helps keep their serrated edges razor-sharp, scientists have determined. This adaptation certainly makes it easier for the animals to hunt and eat prey. Scientists suspect that dinosaurs also had a layer of iron on their teeth. The study, led by scientists from King's College London, sheds new light on how Komodo dragons keep their teeth wear-resistant and razor-sharp. It also provides clues as to how dinosaurs such as Tyrannosaurus rex killed and ate their prey. The results in a description of the study were published in the journal Nature Ecology and Evolution. The Komodo dragon, Varanus komodoensis, is the largest living lizard. It is sometimes called the Komodo dragon. The species is endangered. According to the International Union for Conservation of Nature, there are only about 3,500 Komodo dragons left in the wild. The Komodo dragon can weigh up to 90 kilograms and grow to 3 meters long. These animals are strong, fast, and can take on prey much larger than themselves. But they will also be content with smaller prey. They eat almost any kind of meat, from smaller reptiles and birds to deer and horses. But Komodo dragons have another impressive feature. Their razor-sharp teeth, of which they have 60 and replaced throughout their lives, are covered with an iron coating, which helps them in hunting. New studies of the teeth of these powerful predators have revealed layers of iron along their serrated edges. There is so much iron in their teeth that they are colored orange. Many reptiles have some iron in their teeth, but crocodiles and other lizards, for example, have little of it and it is often invisible. It is not only reptiles that have enriched their teeth with iron. Cryptochiton stelluri, a type of mollusk, has also adopted this strategy. It uses its teeth to scrape rocks to collect algae and bacteria. The iron in its teeth allows it to preserve them for a long time. To understand the chemical and structural composition of Komodo dragon teeth, scientists searched museums for their skulls and teeth. They also examined the teeth of Ganus, a 15-year-old Komodo dragon from London Zoo who was euthanized in February 2023 after being diagnosed with incurable degenerative arthritis. Advanced imaging and chemical analysis showed that the animals have concentrated iron along the cutting edges and tips of their teeth. This protective layer keeps the serrated edges of their teeth sharp and ready to use at a moment's notice. The iron also makes their teeth exceptionally hard and resistant to wear. What's more, the iron coating is also resistant to acids. This could be beneficial to the lizards. The animals regurgitate hair, horns, and other indigestible food, exposing their teeth to their own digestive acids. This research opens up new questions and avenues for research into how extinct species such as dinosaurs lived and fed. Komodo dragons have curved, serrated teeth that they use to tear apart their prey, just like carnivorous dinosaurs. We want to use this similarity to learn more about how carnivorous dinosaurs may have fed, and whether they used the iron in their teeth in the same way as Komodo dragons, said Aaron LeBlanc of King's College London, the study's lead author. Unfortunately, with the technology we have right now, we can't tell whether fossilized dinosaur teeth had high levels of iron or not. We think that chemical changes during fossilization obscure how much iron was present at the beginning. The researchers found that larger carnivorous dinosaurs, such as tyrannosaurs, changed the structure of the enamel itself on the cutting edges of their teeth. While Komodo dragons changed the chemical composition of their teeth, some dinosaurs changed the structure of the enamel to maintain sharp cutting edges. With further analysis of the teeth of Komodo dragons, we may find other markers in the iron coating that are not changed by fossilization. Such markers will help determine whether dinosaurs also had iron-coated teeth, LeBlanc said. In search of a method to clean the Baltic Sea of chemical weapons. According to estimates, there are about 40,000 tons of chemical weapons lying on the bottom of the Baltic Sea. These are all remnants of World War II. Various institutions and organizations have been trying for years to find a way to dispose of this deadly cargo. David Kramsky from the Wrocław University of Science and Technology will test the new method. The researcher will check whether popular polymers used in 3D printing can be used to remove arsenic lying on the bottom. David J. Kramsky from the Doctoral School of the Wrocław University of Science and Technology received a grant of €30,000 from the Organization for the Prohibition of Chemical Weapons, OPCW, which will allow him to check whether popular polymers used in 3D printing, after appropriate chemical modifications, can be used to remove arsenic lying in the Baltic Sea. And there is a lot of it there. According to the Mayer Foundation, there are approximately 40,000 tons of chemical weapons lying on the bottom of the Baltic Sea, of which at least 15,000 tons are toxic warfare agents, CWS, mainly sulfur mustard or arsenic, but also chlorite, chloride-2, adamsite, chloroacetophenone and tabun. In addition, there is a difficult to estimate amount of conventional weapons, aircraft bombs and mines. These are all remnants of World War II. Chemical weapons dumps from World War II are a significant source of arsenic in waters and bottom sediments. Arsenic from decaying chemical weapons is a serious threat to the marine ecosystem and human health, emphasizes David Kramsky, who in his project wants to propose an innovative approach to the disposal of sunken war waste. The idea of producing and testing a material for removing toxins, printed on a 3D printer, came to him during research for his doctoral thesis. In it, he deals with the topic of heavy metal removal on modified structures printed in 3D technology from polymer materials. My concept assumes obtaining an optimal structure, e.g. a filter, printed on a 3D printer from commonly known and used polymers, e.g. PLA, ABS, PTGE, PC. Their advantages are that they are both easily available and cheap to obtain, explains our PhD student. The next step in his project will be chemical modification of the print surface so that it acquires sorption properties. Here, the key will be for the young researcher from WUST to develop a method so that the obtained structure has an affinity for specific pollutants, i.e. catches them, and in the case of his grant, for arsenic. Appropriate material properties will cause interventional or permanent absorption of seawater pollution, which in my opinion is an attractive alternative to the methods used so far, which involve extracting and destroying sunken chemical weapons, explains David Kramsky.